Hi, my name is Jindřich.
And I'm Indra Helso.
We're from Charles University in Prague.
And this is our paper, Lexically Grounded Subword Segmentation. Subword segmentation methods, like sentence piece or BPE, are widely used in NLP models for their efficiency, but they struggle with capturing language morphology. In this paper, we try to fix it.
The usual approach to subword tokenization consists of
pre-tokenization into word-like units,
statistical vocabulary learning using byte pair encoding or the unigram model,
and finally segmenting the word-like units into subwords using the corresponding algorithm.
In our paper, we propose 3 innovations. First, we use Morfessor, an unsupervised morphological segmenter, as a part of pre-tokenization.
Second, we show an algebraic solution on how to extend the skipgram model for subword embeddings and use them for tokenization.
Finally, we distill the embedding-based model into a fast bigram model, a straightforward generalization of the sentence piece unigram model.
So we don't need to use Morfessor and the embeddings at inference time.
We extend the skipgram model to assign embeddings to subwords based on what words are in their context window. The original skipgram model approximates this equation. The softmax of the product of the input embeddings and the output embeddings should be equal to the normalized co-occurrence matrix C, where Cij says how many times word J appeared in the context of word I, and normalizing the matrix row-wise gives us the corresponding probabilities. Further, we define matrix A, which says what subwords appear in words in the vocabulary. Multiplying A and C gives us the co-occurrence of subwords with words in a context window. With that, we can formulate the skipgram equation for embeddings. This matrix normalized should be equal to softmax of the subword embeddings times the output embeddings that we already know. We can solve this equation now for ES for the subword embeddings. So the subwords embeddings are equal to the logarithm of the normalized co-occurrence matrix of subwords and words times the right inverse of the output embeddings from the skipgram.
Now that we have the recipe for computing subword embeddings, representations of both words and subwords fall into the same vector space. And now, when we want to segment a word, the only thing we need to do is to use subwords which are close to the word in the shared vector space. And that's it. In our implementation, we find the best sequence of subwords using dynamic programming. In theory, our method allows us to assign embeddings to all substrings of words in the dataset. To limit the size of the subword vocabulary, instead of all substrings, we initialize it with a set of subwords obtained by running either BPE or the unigram model. After this step, we iteratively segment the vocabulary using the subword embedding-based algorithm, and then we recompute the subword embeddings based on the newly obtained subword co-occurrence matrix.
Now, because the embedding-based algorithm requires running Morfessor and storing big embedding tables, we introduce another segmentation algorithm. We segment the entire embedding vocabulary using the embedding-based algorithm and compute statistics of subword bigrams. Using those statistics, we find a segmentation that maximizes the bigram probability. Because finding the exact solution is quadratic in the word length, we approximate the inference using beam search. We conduct 3 sets of experiments to verify how well our tokenizer works in practice. First, we do intrinsic evaluation for morphological plausibility. Second, we experiment with part-of-speech tagging. And finally, we experiment with machine translation on the IWSLT 2017 data. In our intrinsic evaluation for morphological plausibility, we use test data from the Sigmorphone 2018 share task for Czech, English, Spanish, French, Hungarian, Italian, Mongolian, and Russian, which contains gold segmentation for words from those languages. We use 50 million sentences from NewScroll to train fast-text embeddings for our embedding-based segmentation, with the exception of Mongolian, for which we use smaller amount of data from CC100 corpus. We use BPE and unigram for vocabulary learning. And finally, we measure the morpheme boundary precision because we want our algorithm to make correct splits of the words, but we don't care if morphemes are merged into bigger units. When we look at the results for the 32,000 vocabulary averaged over the languages, we can see a big improvement over the BPE and unigram model when using the word-like tokenization. Using Morfessor as pre-tokenization further improves the boundary precision, and so does our segmentation method. When we look at the breakdown into individual languages, we can see that Morfessor plus our tokenization is still the best, but it depends on the languages whether it is better to use unigram or BPE for vocabulary construction. When we look at different vocabulary sizes, when we look at the results for different vocabulary sizes, we observe that precision increases with the vocabulary size because we do less splits. And we see that our methods improves compared to using just BPE or unigram for all vocabulary sizes. The recall decreases with the vocabulary size, and so does the F1 score on the morphological boundaries. Our second set of experiments is on part-of-speech tagging. We use universal dependencies corpora for that, and we use the same set of languages as we did in the intrinsic evaluation, with the exception of Mongolian, which does not have a UD corpus. Our tagger is a simple neural network with 2 bidirectional LSTM layers with 600 units and embeddings of 300. And we compare different subwords with words and Morfessor vocabulary. When we look at the results, we see that using subwords is better than using words or morphemes from Morfessor. And we also see that the Morfessor pre-tokenization helps, especially for Hungarian. And our tokenization consistently improves over both BPE and unigram. In the machine translation experiments, we use IWSLT 2017 dataset with 18 language pairs with different combinations of Arabic, English, Dutch, German, Italian, and Romanian. We use the transformer-based architecture as implemented in Marion, and we use 3 vocabulary sizes, 4,000, 8,000, and 16,000. We use 8 different tokenization techniques, which means we have 24 models per language pair, 332 empty models in total, and we evaluate our models using the character F-score. When we look at the results, standardized and average over the 18 language pairs, the results look like this. Morfessor pre-tokenization does not help, neither does our tokenization and the word-like pre-tokenization setup. It slightly helps when using Morfessor, but the good old unigram and BPE tokenization was still the best for machine translation. To summarize, we developed a subword segmentation algorithm that involves Morfessor for pre-tokenization and subword embeddings to better preserve lexical meaning. We distill our tokenization pipeline into a fast bigram-based algorithm that does not use Morfessor and embeddings at inference time. Our tokenization better preserves morphologic. It works well for part-of-speech tagging, but we did not observe any improvements in machine translation.